This slide set is about IPv6 management. Similar to IPv4, there is a set of management protocols related to IPv6. The first one is ICMP version 6, which has tasks similar to ICMP, but some additional tasks have been integrated into ICMP version 6. One of them is the Neighbor Discovery Protocol that uses ICMP version 6 messages. NDP replaces the Address Resolution Protocol. One important aspect of the NDP specification has been the auto-configuration, so that some way of configuration is already possible without DHCP. Nevertheless, there is also DHCP version 6, which is comparable to DHCP, but there are some differences in the details. Additional modifications are necessary in the DNS to support for mobile users and in the routing protocols OSPF and ISIS. On this slide, we take a closer look at ICMP version 6. Similar to IPv4, it provides error messages and status messages. Therefore, the protocols ping and trace route work in the same way for IPv6. Since IPv6 often uses multicast, ICMP v6 can administrate the multicast groups. Closely related to this point is the auto-configuration of IPv6 addresses, where special messages to search for routers or neighbors are defined. The technical terms are solicitation for requests and advertisement for responses. Support for mobile users is also realized via ICMP version 6. In the following slides, we investigate the address configuration concept. The general idea is that this configuration should happen on the devices on their own as much as possible. The stateless auto-configuration does not involve a DHCP server. This is in particular interesting for Internet of Things scenarios where many devices should be able to communicate without much administrative effort. The procedure works as follows. A device can generate an IPv6 address on its own. It uses a special network prefix FE80 and combines it with an interface ID that it has derived from its MAC address. We see more about this on the next slide. The IPv6 address is announced by the device in the subnet to detect whether another device already uses this IPv6 address. For doing so, a special multicast address space is reserved and the device attaches 24 MAC bits at the end of it. If there is no reply by another device, then the IPv6 address is not in use yet and the device can search for a router in the subnet. For this purpose, a special multicast address is available. The router replies via another special multicast address to provide the routing prefix, which holds for the subnet. The device can then use the learned routing prefix and the interface ID so that it constructs a globally valid IPv6 address on its own. On this slide, we see how it is possible to generate an interface ID based on the MAC address. This is called the modified EUE64 format. You basically take the 48 bits of the MAC address and extend it to 64 bits by inserting a well-known bit sequence in the middle. The universal local bit in the company ID part is set to 1. The procedure on the previous slide is not mandatory, so that the address generation can also be solved in a different manner. However, it is recommended because it allows for an automated IPv6 address generation. In addition to the stateless auto-configuration, there is the stateful auto-configuration, which requires a DHCP version 6 server. The initial configuration requires that a device has already generated a locally valid IPv6 address on its own. as we know it from the first steps of the stateless auto-configuration. After that, this device searches for a DHCP v6 server for which again a specific multicast address is available. There can be one or more DHCP servers that offer addresses based on this request. As discussed in the DHCP video, running two DHCP servers in parallel can be useful so that one DHCP server does not become a single point of failure. The device selects an offered IPv6 address and replies to the DHCP v6 server via the special multicast address. Then the DHCP v6 server provides all required configuration data like default router and DNS servers. In the context of DHCP v6, there are several ways how to actually implement it. For example, so-called stateless DHCP v6 is also possible, where the DHCP v6 server just provides the additional configuration data but no IPv6 address. In this case, it does not have to administrate addresses that it provided before. In the context of IPv6, there are two major privacy issues. One problem exists if users apply the presented method to derive the interface ID from the MAC address. Since the MAC address is unique worldwide, users become identifiable in every network. Therefore, a method called privacy extensions has been specified. It changes the interface ID periodically and includes a timestamp and a hash function into the calculation. Another problem can occur for private users when they access the internet from home, for example via their DSL access. Now the /64 network prefix that the user has can be abused to track the user actions. It does not make a difference whether the user applies the privacy extension method. To cope with this problem, the user has to rely on the provider so that the provider supplies another /64 network prefix from time to time. As you know, the transition between IPv4 and IPv6 is already ongoing for some years and will also continue some more years. Nowadays, you find therefore often situations where IPv4 and IPv6 are used in parallel. One scenario is called dual stack. In this scenario, devices implement both IPv4 and IPv6. For instance, if a router receives an IP packet, it checks at first whether it is an IPv4 or IPv6 packet and then processes it according to the IP version. Dual stack is an established method for routers and servers. In some reports, it is not recommended for clients, even though modern operation systems should be able to deal with this way of configuration. A scenario relevant for home users is called dual stack lite. Here the user gets a globally valid IPv6 network prefix, but the IPv4 address is not globally valid because the provider uses NAT. This is not the NAT that the user implements, but an NAT inside of the provider network. Then there are many possibilities for configuring tunnels. An example scenario is that you have two IPv6 only networks and you want that they can communicate via an IPv4 only network. In such a case, IPv6 packets can be transferred as payload of IPv4 packets. Finally, there are translation mechanisms where IPv4 addresses are mapped onto IPv6 addresses. On the final slide, we see an example for the NAT64 DNS64 mechanism. As you can see, there is an IPv6 only and an IPv4 only network. An IPv6 only computer wants to communicate with server example com and does a DNS request for this purpose to a DNS server to learn the IPv6 address of the example server. The DNS server is a special DNS64 server and translates this request to an IPv4 request to the proper DNS server in the IPv4 only network. This DNS server replies with the IPv4 address, which is translated by the DNS64 server to an IPv6 address. This IPv6 address uses a special beginning 64 and so on. The computer does not know that there is anything special about this IPv6 address and uses it to start a TCP connection to the server. SYN is the start of a TCP connection. The router is a special NAT64 router which recognizes the special IPv6 address and translates the IPv6 packet to an IPv4 packet. In summary, this method is quite smart because devices inside of IPv4 only and IPv6 only networks do not notice anything of the translation and do not have to be reconfigured.